All right. This one is one of those that they love to do with conservation of energy and momentum all thrown in together. So cart A right here has a mass of m and is released from rest at a height of 2h on a ramp making an angle of 2 theta with the horizontal shown above. Cart B has a mass of 2m and is released from rest at a height h on a ramp making an angle theta with the horizontal. The carts roll toward each other and have a head-on collision with the on the horizontal portion of the ramp and stick together. So it is a completely inelastic collision. The masses of the cart's wheels are negligible, as are friction or drag forces. You might wonder what the masses of the wheels are. We probably haven't gotten to this at the point of this covering this video, but it turns out the masses of things rotating matters. Um, so we don't have to worry about that. So indicate whether the carts remain at rest, move to the left, or move to the right after the collision. Explain how you arrived at your answer. So first thing is, we're going to have to get the speed of this cart as it gets down to the bottom, and same thing for this one. So anytime you have something on a ramp and you want to know the speed when you get to the bottom, you use conservation of energy. So to set that up, whoops, let me pull that down just a smidge there. So we have gravitational potential energy here, and that's going to change into kinetic energy. So let's set this up, each equation. This will be mgh, generic h, by the way, and this will be 1/2 mv squared. The m's cancel, and so when we go to solve for the velocity, and maybe you've got this memorized, but it is a free response, you'll have to show it. The velocity is 2gh square root of all of that. That's a generic h, by the way. Notice it's got nothing to do with this angle. That angle doesn't matter at all. They're being jerks. They're trying to throw you off here. So let's plug it actually in for cart A. So when cart A gets to the bottom, we can figure out its velocity. The velocity of A will be 2 radical 2g 2h. So, and I can clean that up a little bit since there's 2 2's there. I can pull that out. So 2 radical gh is its speed there. Let's do the same thing for cart B. So we can save some time now. We don't have to show that again. So its velocity when it gets to the bottom will be radical 2g, and its height is actually h there. So that is its speed. So 2 radical gh and square root of 2 radical gh. So now when they get down here and they're going to collide, that becomes a conservation of momentum problem. And so let's see what happens to the total momentum. I'll need another sheet. It's getting full on this one. So let's put this here. So cart A was going to the right like that. Its momentum will equal its mass times its velocity. So its momentum, its mass is m, and its velocity, if you remember, was 2 radical gh. Cart 2 was going the other way. Its momentum will be its mass times its velocity. So its momentum then is, its mass is 2m, and its velocity was radical 2gh there. And by the way, it's negative to indicate that it's going to the left. So which one is bigger? Because that's going to determine whether or not, if they're equal, it will just boom, hit and stay. If this one's bigger, boom, they'll hit and move off to the right. If this one's bigger, boom, they'll hit and move off to the left there. So you can see here, they each have an m outside, so don't worry about that. They've each got a radical gh, so don't worry about that. So just look at this. This one is a 2, and this one's got a 2 as well, but a radical 2 left over. So this one is bigger. So overall, the momentum is to the left. And that means when they collide and stick together, that overall they're going to move to the left there. All right, part B. It says, consider the time interval from when the two carts are released until just after they collide for the system consisting of the two carts and Earth So whenever they include Earth, we can talk about gravitational potential energy. Indicate whether the total mechanical energy increases, decreases, or remains the same. So here's the thing, and people get this confused. There's sort of two parts. As the carts come down onto this level part, the mechanical energy stays the same because we're just converting gravitational potential energy into kinetic energy. But when they collide and they all stick together, that, by definition, when they stick together, is an inelastic collision. It is a perfectly inelastic collision. And in an inelastic collision, we lose kinetic energy. So the system will actually have its energy decrease in that case. Where did it go? Heat, sound, maybe the objects deformed as they hit each other and stuck together. So that is why that they decrease for the system being the two carts and the Earth there. So second part here says, for the system consisting only the two carts. So that means no gravitational potential energy. Rather than thinking of it as energy we already had, we will think of gravity as doing work on the system, which will change their kinetic energy. So indicate whether the total mechanical energy decreases, increases, or remains the same. Well, here's the simple way. There was no movement right at the moment you release them, so the kinetic energy was 0. And there is movement even after they stick together, so kinetic energy does not equal 0. So overall, the system increased. You might say to yourself, well, what about the whole inelastic collision? Well, it lost energy in the collision, but we gained energy coming down here, and we lose it here, but overall the gain was bigger. So let's just pretend we gained 20 joules, and here we lost 15 joules. The net gain would still be 5 joules there. But the easiest way to describe it is right here. Nothing was moving before, things were moving afterwards. So the work that gravity did on the system, that increased our kinetic energy more than the kinetic energy we lost in the inelastic collision.